In this tutorial, we are going to study three particular points, and they go like: first, we are going to study shearing transformation. Then we are going to get an overview of composite transformation. Composite transformation means a transformation technique where more than one transformation is involved in a single transformation. Then we will get an overview of transformation with respect to some arbitrary point. If you carefully observed the studies what we have made until now, you can find that for all the transformations, our pivot point, or the point with respect to which transformation has been made, was the origin. Now say you want to perform the transformation with respect to some point other than origin, and the goal of this last point is to get an overview of that thing. Now let's start with shearing transformation. Now at the beginning, have a look at the definition of shearing transformation. Shearing transformation in two dimensions is an ideal technique to change the shape of an existing object in a two-dimensional plane. So the main goal of this shearing transformation is to change the shape of an existing object, and you have to do this in a two-dimensional plane. Now in a two-dimensional plane, what happens is the object size can be changed along x direction as well as in the y direction. So to get a visual representation of this point, let we draw a rectangle object. Now this blue rectangle, say ABCD, is the original object onto which you want to apply shear transformation, or you want to change the shape of this rectangle. Now you can see that its shape can be changed either along x direction. You can see that this red polygon we can get by applying a force onto this polygon along the x-axis. If you grab the C point and pull it towards this direction, you will get a shape like this. Or you can change its shape in the y direction as well without changing its shape towards x direction. For that, you have to pull this rectangle in the upward direction by grabbing the C point. So this was a visual representation for this property. In a two-dimensional plane, the object size can be changed along x direction as we did in case of this red polygon, or in the y direction as we did in the green polygon. So how this shearing in x-axis and shearing in y-axis will go like, to find this we have to dive deeper. So have a look at the individual cases. Here is your original object. So let me draw the x-axis with blue color, and the original object goes like A, B, C, D. Now, in this diagram, you can see that shear force or shearing transformation has been applied to this rectangle ABCD to get the polygon A dash, B dash, C dash, D dash. Now you can see that in case of shear in x direction, only x coordinate values for the vertices has been changed and no change has taken place along y direction. You can see that for the points A and B, original locations are preserved and the object shape has been changed in terms of point C and D, where C and D point have been right shifted. That means the x coordinates for point C and D has changed, but there are no changes in the y direction. Now, in this diagram, you can see an example of shear transformation in y direction. Now, in case of shearing in y direction, what happens if you follow? You will find that there is no change in x coordinate values. Only changes which have taken place are in the y coordinate values. Let me define the polygon in terms of A double dash, B double dash, C double dash, and D double dash. For all the four vertices, you can see that x coordinate values are same as that of original polygon ABCD. The x coordinate value for A is same as the x coordinate value for A double dash. X coordinate value for B is same as the x coordinate value of B double dash. X coordinate value of C is same as the x coordinate value of C double dash. I should have put double dash here, and so on. But y coordinate values for B and C has been changed in case of B double dash and C double dash. So in this case, what happened? In this case, the shape of the object, existing object, that is ABCD, has been changed in the y direction. That means this is an example of shear transformation in y direction. Now come to this diagram. You can see that in this diagram the shape has been changed both in x direction and y direction. That means this is an example of shear transformation in both directions. Now let me dive deeper into this shearing transformation to get some mathematical idea of this particular transformation. So shearing in x-axis is achieved by changing the x coordinate value of the point in question. So to explain explicitly, I will say that in your 2D space, and here is a point xy, x old, and y old onto which you want to apply the shearing transformation. Now, from our previous discussion, you can say that if you apply shearing transformation along the x direction after transformation, there will be no change in y coordinate value. So you can see it here that when you define this mathematically, y new equals to y old. That means y coordinate value have not changed. Now, x coordinate value will be changed by a factor called shearing factor along x-axis, which is defined by SHX. So SHX, you can term it as shearing. Let me drag it. Uh, Transformation factor along x-axis is SHX, and the equation goes like x new equals to x old. That means your original x coordinate value plus SHX multiplied with y old. Now, if you convert these two equations into matrix form, you get something like this: x new, y new equals to 1 SHX, and in the next row you have 0, 1 multiplied with x old, y old. If you multiply this right hand side, you will get x new equals to x old multiplied with 1, that is x old, plus SHX multiplied with y old. So you get this x new value. Then y new goes like 0 multiplied with x old plus 1 multiplied with y old. So at the end you get y new equals to y old. So this is your shearing matrix in 2 dimensions, but without involving any homogeneous coordinate system. Now, if you want to convert this to homogeneous coordinate system, then your shearing matrix will be like x new, y new, 1 equals to 1 S H X 0 0 1 0 0 0 1 multiplied with x old, y old 1. Once again, if you multiply the right hand side of this equation, your end result will be these two equations. So this was the homogeneous representation for shearing along x-axis. Now let me have a look at the shearing transformation along y-axis. If you can recall, you can say that when you apply shearing transformation along y-axis, then there no changes take place in the x coordinate value. So your x new, that means transform x coordinate of the transform point will be equal to the x coordinate of the original point, and y new will be equal to y old plus SHY multiplied with x old. So this SHX is your shearing transformation parameter along y-axis. So in matrix format, this equation will go like x new y new equals to 1 0 is, and at the next row shy 1 multiplied with x old y old. If you solve the right hand side multiplication, you will get back to this original equations. 1 multiplied with x old plus 0 multiplied with y old equals to x old, which is the value of x new after transformation, and for y new you will get x old multiplied with shy, this one, and plus y old multiplied with 1. So this was again the non-homogeneous representation or Cartesian representation for shearing matrix along y direction. Now to convert the system of equations into homogeneous system, like all the previous instances, you have to introduce a 1 equals to 1 into your equation system. Now if you convert this three equations to a single matrix equation, you will get something like this: x dash equals to x, y dash equals to y, plus shy multiplied with x equals to 1 equals to 1, and this implies x dash y dash 1 equals to 1 0 0, and at the next row shy 1 0 0 0 1 multiplied with x y 1. So this is your shear matrix along y direction. If you solve the right hand side multiplication, you will get back to this three equations. Now here is a problem for you which you should try to solve after going through this shearing transformation tutorial. And the problem goes like, given a triangle with points 1 1 0 0 and 1 0, apply shear parameter 2 on x-axis. That means your SHX is 2 and 2 on the y-axis. That means your SHY is also equal to 2, and your goal is to find out the new coordinates of the object. Try this yourself and try to find the result. Now this was all about shear transformation in 2 dimensions. Next, let we move to composite transformations. Here are the basic transformation matrices at one place in homogeneous coordinate system. Here you can see the translation matrix in homogeneous system. Here you can see the rotation matrix, and here you can see the scaling matrix respectively. Let me move forward to composite transformations. So composite transformation is what? Composite transformation is something where you apply more than one transformation to a particular object. And if you look into the first example, which involves translation into the transformation sequence, you can find that you have a point object P into your 2D space. Here you have a point P into your 2D space. Now the problem goes like, you have to apply a translation by an amount T1x and T1y to this point P. Now after this translation, you will get a transformed point. Now onto this transform point, you have to apply a second translation, and at this time by an amount of t2x and t2y. So on a whole, what is your transformation? These two translations make your entire transformation. That means at first you have to translate this point by an amount of say tx, t1x and t1y. So by applying this transformation, your resulting point P dash will be somewhere here. Then onto this P dash, you have to apply this translation once again by an amount of T to X and T to Y to get the resulting point P double dash. So this is the idea behind composite transformation. So if you know the entire sequence of transformations which are on its way, you can represent your transformation matrix like this by combining these two transformations. One thing important is you must keep in mind the sequence of transformations in which they need to be applied on the point. Explicitly speaking, the problem was that you have to apply translation by an amount of t1x, t1y first, then you have to apply the translation by an amount of t2x, t2y. So what you cannot do is you cannot multiply this point P with this second translation matrix before this translation matrix. You have to apply this translation first, then on the resulting point you have to apply this translation. If you want to apply the transformations individually, and if the transformations are of same type, then you can combine these transformations to get a single transformation matrix. Here you can see an example which did the same thing with rotation. A point was first rotated by an angle of phi, then the resulting point is again rotated by an angle of theta. Here we have an example which involves scaling. You can see that first a point has been scaled by an amount of s1x and s1y. Then the resulting point from this scaling has been scaled once again by an amount of s2x and s2y. This was the idea behind composite transformation, where on a point you apply more than one transformation. Now let we move to transformation with respect to some arbitrary point or a pivot point. So let me formulate our problem statement first. And what does it mean to apply a transformation with respect to some arbitrary point? Until now, whatever we have studied, say you have a point xy in your two-dimensional space onto which you need to apply a translation by tx and ty. Now, what is explicit in this problem statement is that this translation has to be applied with respect to the origin. Or in other terms, when you say the problem like this, say apply a translation by tx and ty onto point xy, you originally are saying that your coordinate system has 0, 0 as its origin. Now, say if I say translate this point xy with respect to point xt and yt, then how the problem will go like? You can imagine the problem something like you have another coordinate system which has xt and yt as its origin. Now, as you know, our matrices or translation matrix has been derived in terms of a coordinate system which has 0, 0 as its origin. Now your origin is xtyt. So what you can do? You can translate this entire space defined in terms of xtyt as its origin to the space which has 0, 0 as its origin. To do this, what you have to do? You have to do a translation by an amount of minus xt and minus yt to move this point xt, yt and all the points associated with its reference frame to the origin. So once you did this, now you can apply your original translation matrix to the resulting points. Once you do this, then do a reverse translation. For what? You have to translate everything back to the coordinate system which has been defined by xt, yt as its origin. You can see an example here. Here it is being told to rotate a point P by or with respect to the point xr, yr. So what is being done? First, this point P is translated by an amount of minus xr and minus yr. By applying this translation, you are getting the relative location of this point with respect to origin. Then you do what? You rotate this point with respect to the origin by an angle of theta. But this rotation was done with respect to the origin 0, 0. Now you have to do what? You have to translate back everything to xr, yr. So you will translate the point which you have got after rotation by an amount of xr, yr. So here is the composite transformation sequence. First you have translated by an amount of minus xr minus yr, then you rotated it, then you have applied a translation by an amount of xr yr to put everything at their original place. So this is an example or application of composite transformation where you do the transformation with respect to some pivot point. Here is an example of scaling with respect to some arbitrary point, say with respect to xf, yf. You can see that here also same thing has been done. First, entire system has been translated by an amount of minus xf and minus yf to move everything back with respect to 0, 0 as the origin. Then the scaling was done. Then you did a translation by an amount of xf and yf to put everything at their original place. So this was scaling with respect to some arbitrary point. Hope you have learned something if you have observed everything carefully.